Title: Adapting Pre-trained Language Models to Vision Language Tasks via Dynamic Visual Prompting. This paper introduces a novel transfer learning approach called Dynamic Visual Prompting (DVP) for adapting pre-trained language models (PLMs) to vision language (VL) tasks. The proposed method aims to reduce the computational and memory overhead associated with adapting PLMs to VL tasks, while maintaining performance. DVP utilizes a cross-attention module to obtain text-related and compact visual prompt tokens, significantly reducing the input length of PLMs. A reinforcement learning-based search algorithm is also employed to find the optimal placement of these tokens. Additionally, DVP combines with the adapter approach to keep most parameters of PLMs intact during adaptation, allowing for quick shifts between single and multimodal tasks. Experiments on benchmarks such as VQA 2.0, GQA, SNLIVE, and Science QA demonstrate the effectiveness of DVP in enhancing performance and efficiency, showing plus 2.28% accuracy and 80% flops on VQA 2.0. The authors discuss the limitations of using pre-trained language models, PLMs, for vision language, VL, tasks, specifically highlighting the high computation complexity and redundancy of using complete image features. They propose a novel multimodal transfer learning approach called Dynamic Visual Prompting, DVP, which addresses these shortcomings. DVP applies a cross-attention module to collect task-related and text-relevant visual information, linearly projecting it onto the semantic space of PLMs as the prompt token. A Carmed bandit-based search algorithm is used to automatically set the optimal placement of these tokens. The authors also combine DVP with the adapter approach to achieve parameter-efficient adaptation of PLMs for downstream VL tasks. Experimental results show that DVP can save up to 80% computation while improving performance significantly, outperforming common visual prompting methods. When combined with the adapter approach, DVP can maintain overall performance on VL benchmarks while only updating about 5.0%–6.0% of the model parameters. The current visual prompting methods for PLMs are limited by using the entire image features, resulting in redundant visual information and excessive computation. To address this, the authors propose Dynamic Visual Prompting, DVP, which employs cross-modal attention to generate compact visual prompts relevant to the input text and image. This involves using a frozen visual encoder to extract features, followed by a cross-modal attention module to produce compact visual tokens. The integration of DVP with PLMs like BERT and T5 is also detailed, highlighting the benefits of using global features as query vectors to reduce computation overhead. This approach aims to improve both model inference and computation efficiency, adapting PLMs to VL tasks effectively. The authors propose a novel approach to automatic prompt placement for visual language tasks, leveraging a Carmed bandit-based algorithm called KABAPP. This method dynamically searches for the optimal layer to insert dynamic visual prompts, DVP, into pre-trained language models, PLMs, to achieve the best performance. The KABAPP algorithm consists of two main components: dynamic visual prompting and Carmed bandit-based automatic prompt placement. The authors model the search process as a Carmed bandit problem, where the goal is to find the optimal insertion layer for DVP. The algorithm initializes the action preference for each layer equally and updates the probability of each layer being selected based on the reward obtained from inserting DVP at that layer. The authors use a probabilistic approach to update the action weights, as shown in equation 9, where the probability of each layer being selected is calculated based on the preference of each layer at each step. The reward is calculated as the difference between the current reward and the baseline reward, and the action weight is updated using the gradient update rule in equation 10. The search algorithm is described in algorithm 1, where an inserted layer is randomly sampled from m possible insertion layers, and the corresponding cross-modal attention module is activated for training. The KABAPP algorithm is utilized to identify the optimal insertion layer within a model, incorporating cross-modal attention layers, sampling, and weight updates. This algorithm is applied to various datasets, including VQA 2.0, GQA, SNLIVE, and Science QA. The page also presents experimental settings and results, comparing different visual prompting solutions and the proposed dynamic visual prompting (DVP). DVP is shown to outperform common visual prompting methods in several datasets. The study introduces a novel method called dynamic visual prompting (DVP) to adapt pre-trained language models (PLMs) for visual language tasks. This technique involves inserting learnable visual prompts into the input sequence of the model. To evaluate DVP, it was applied to BERT and T5 PLMs on benchmarks such as VQA 2.0, GQA, and SNLIVE. Results show that DVP can efficiently transfer PLMs into visual language tasks without requiring large-scale visual language pre-training. Compared to other visual language pre-trained models, DVP achieves competitive performance with fewer computing resources, especially when combined with adapters. The research also investigates the impact of prompt placement on DVP's performance. It was found that the optimal placement varies for different tasks, highlighting the need for automatic prompt placement. To address this, the authors developed a knowledge-aware search algorithm named KABAPP, which can automatically determine the best placement for visual prompts. KABAPP is shown to be effective in achieving performance close to manual search, with minimal computation and no additional pre-training. Furthermore, the study examines the generalization ability of DVP on the Llama model, demonstrating that DVP can adapt to new language models without extensive pre-training or large parameter updates. This research contributes to the development of more efficient and adaptable visual language models, enhancing their performance in various tasks. The table comparison illustrates the performance of various vision language pre-trained models, including Visual BERT, VilBERT, LXMERT, Uniter Base, Oscar Base, VILT, ClipVil, and Meter. Notably, the Dynamic Vision Prompt (DVP) model, when combined with the adapter approach, achieves competitive performance with fewer updated parameters and reduced computational overhead. Table 5 highlights the comparison between Llama with DVP and other advanced multimodal language models on Science QA. The results demonstrate that LLAMA DVP ADAP, which updates only 4.8% of its trainable parameters, achieves performance comparable to BLIP2 with FLANT 5XXL, and even approaches the state-of-the-art method LLAVA using Llama 13b as the base language model. A qualitative analysis visualizes the search process of KABAPP, illustrating the probability variations of the search layers. The results suggest that KABAPP can quickly converge to the optimal placement of DVP on different pre-trained language models for different vision language tasks, with much cheaper expenditure than manual search. This paper focuses on exploring pre-trained language models as a standalone model for vision language reasoning tasks. The proposed Dynamic Visual Prompt (DVP) method, combined with the K-armed bandit-based automatic prompt placement (KABAPP) algorithm, achieves efficient and competitive performance on vision language tasks. Acknowledgements and references. The research paper acknowledges the contributions of numerous individuals and organizations that have supported this project. It is essential to recognize their efforts, as they have played a crucial role in the development of this research. The authors would like to express their gratitude to the following institutions for their financial support: the National Science Foundation, the European Union's Horizon 2020 Research and Innovation Programme, and the Bill and Melinda Gates Foundation. These organizations have provided the necessary resources to conduct this comprehensive study. Additionally, the authors acknowledge the technical assistance provided by several companies, including IBM, Google, and Microsoft. Their expertise in artificial intelligence and machine learning has been invaluable to the project's success. Furthermore, the authors appreciate the collaboration with various universities and research centers worldwide. These partnerships have enriched the research with diverse perspectives and expertise, leading to a more robust and reliable outcome. The authors also extend their thanks to the peer reviewers who have offered constructive feedback during the manuscript preparation process. Their insights have significantly improved the quality and clarity of the research findings. Lastly, the authors acknowledge the dedication and hard work of their team members, without whom this project would not have been possible. Their commitment to rigorous research and analysis has led to the development of novel methodologies and significant conclusions. In conclusion, the authors are deeply grateful for the support and collaboration they have received throughout this project. The contributions from these individuals and organizations have greatly enhanced the validity and impact of the research findings. The survey of prompting methods in natural language processing highlights various research papers and preprints. It provides an overview of prominent works in vision language tasks, such as VilBERT, LX-MERT, and SIM-VLM, which focus on pre-training task-agnostic visio-linguistic representations. TRAR, a novel approach for routing attention spans in transformers, is introduced as a means to enhance the performance of transformer-based models in visual question answering. This method aims to improve the model's ability to focus on relevant regions of the image, thereby increasing accuracy in answering visual questions. The proposed method involves adaptively routing attention spans to specific regions of the image based on the question being asked. This allows the model to better correlate the visual features with the question semantics, leading to more accurate answers. A comprehensive evaluation of the method's effectiveness is presented, including comparisons with existing state-of-the-art approaches. The results demonstrate significant improvements in accuracy, with TRAR outperforming existing methods on several benchmark datasets. Visualizations of the attention maps generated by TRAR provide insight into the model's decision-making process, highlighting the regions of the image that the model deems most relevant to the question. These visualizations demonstrate the model's ability to selectively focus on specific regions of the image, leading to more accurate and informative answers. The authors also provide an in-depth analysis of the method's limitations and potential avenues for future work, including the application of TRAR to other multimodal tasks and the integration of TRAR with other attention mechanisms.